everybody, how are you? Today we will learn how to produce egg shapes using mathematical functions. But these egg shapes are going to be something special because we'll be using the golden ratio. So if you are ready, let's get started. As I said before, today we will produce egg shapes using mathematical functions, but we will also use the golden ratio. So what is the golden ratio? It's a mysterious number that we keep seeing in all branches of mathematics. But we also see it in the nature. We see it in the spiral galaxies. We see it in the seashell. We see it in the flowers, trees, animal bodies, all over. And it has been being used in architecture and also in the art. It is amazing. So we will use this golden ratio to construct these egg shapes. In mathematics, we say that two quantities are in the golden ratio. These could be like two real numbers, right? If their ratio, let's say A over B, is equal to the ratio of their sum, A plus B, to the bigger of these numbers, A. So here I assume that A is larger than B, right? So this is in golden ratio now. Okay? So A over B is phi. So phi is my golden ratio. So then what I can say is phi is equal to 1 plus B over A. Okay? So then phi is equal to 1 plus 1 over phi. So if I multiply everything with phi, phi squared is equal to phi plus 1, or phi squared minus phi minus 1 is equal to 0. So this is the quadratic which is satisfied by this golden ratio. So this, of course, has two roots, but we'll be looking at the one which is going to be positive, right? So phi, the golden ratio that we are actually looking for, is simply equal to 1 plus square root of 5 divided by 2. So this is called the golden ratio. So as you see, due to the presence of the square root of 5, it is an irrational number. So if you want to look at the first few digits, so it is close to 1.618, and it continues like that. Using this quadratic, actually we can find relations between different powers of this phi. For example, this is really simple to see here. So phi squared minus phi is equal to 1. Okay, this is one of the relations. So if you multiply with this phi, with this equation with phi, we have phi cubed minus phi squared is equal to phi. Or we can write phi cubed minus phi is equal to phi squared. We can even write phi cubed is equal to phi squared plus phi. So there are like different ways of writing the exact same equation using the powers of phi. Now the question is, how can we construct an egg shape using the golden ratio? I will follow a design requirement proposed in another video. I will also put the link to that. I was actually inspired by that video before I came up with my own creations. We will draw an egg shape. So this is y-axis, this is x-axis. So the first design requirement is that the bottom piece here, the bottom part of this egg, is going to be a semicircle. Okay, this is easy. So this is going to be a semicircle, just like that. And the radius of this semicircle would be just phi. Okay? And this is also phi. The top here, the topmost point and the bottommost point. So these are 2 points that are of importance to us. So we require that this distance would be equal to phi cubed. So here comes how the golden ratio actually affects the shape of this egg. This is phi, this distance is going to be phi cubed, right? So what is going to be this distance then? So phi cubed is equal to phi squared plus phi. Or in other words, phi cubed minus phi is equal to phi squared, right? So from here, the origin to the top, this distance would be simply phi square. So these are the basic requirements for the design of this golden egg. We say golden egg because we are using the golden ratio to create it, right? So now the main problem here is to find the function at the top. So we will call the bottom function as y of b. So y of b, let's write it down first, is simply equal to minus square root of phi square minus x square, right? The main goal here is to find what is y top. At this point, we can actually introduce another requirement here. So you want to have something symmetric. So y top should satisfy a certain criteria, right? So y top x must be equal to y top minus x. So there should be a x and minus x symmetry. So whatever that function is, it has to satisfy this symmetry relation. The second requirement would be these points here. So let's call this point to be R. So the right point will have coordinates phi and 0. The left point will have coordinates minus phi and 0. So the top function should also include those points so that we'll be able to connect, right, the whole shape. So this would be the other requirement that we have. We will also have the top point here. So let's call it t. So this t will have coordinates 0 and phi square. So based on these requirements, let's move on and try to see what we can create here. So now our goal is to find this y of t function, which will make this top portion of this egg shape. Okay? So as we see, it cannot be a circle because the top function should be passing through this L, R, and T points. And this distance is phi, this is phi square, right? So we cannot create a circle. It should be something else. So the other option could be a parabola, right? And this is what's actually proposed by others. So let's start discussing if we can have a parabola here. Okay? So y of t is a parabola. So the arms of this parabola is opening downwards. So we should have an minus x squared term. And the y-intercept here is phi square, right? So when x is equal to 0, y of t must be phi square. So there is phi square here. Okay, let's check what this coefficient of x square would be. So when y is equal to 0, we are on the x-axis. So x must be equal to phi or minus phi, right? So when y is equal to 0, x is minus phi or phi. So this is actually the parabola that I would like to use. So this parabola nicely connects L, T, and R points. But my question is, if I place a parabola here, like that, do you think the top function and the bottom function are going to be connecting at L and R smoothly? Okay, this is a really, really important question. So in order to answer that, let's look at the derivative of y as a function with respect to x. So this is equal to minus 2x, right? So I'm looking at the region. So this is my parabola. Okay. Without loss of generality, let's look at the point R here. Okay. And this is my y top, this is my y bottom. So then this is R is at phi and 0. Okay. So let's calculate this derivative at x is equal to phi. So this is phi. So this is simply equal to minus 2 phi. It is less than 0. Why? Because if I look at the top function, right, the slopes are all negative. So at x is equal to phi, the slope would be just negative, right? So just assume this parabola is continuing like that, right? So the slope here would be negative. Okay, this is nice. So if I look at the bottom function, let's look at the bottom function. So what is dyb over dx? Okay. So there is a minus sign here, so minus, then I'll have phi squared minus x squared to the power minus 1/2. Okay, this is to the power 1/2. So this becomes minus 1/2, and I put another 1/2 here. Derivative of the inside of this square root is simply minus 2x, right? So simply I can write this as this 2 cancels this 2, minus cancels this minus, so I'll have x divided by square root of phi squared minus x squared. So if they ask me what is the slope at x is equal to phi, right? So this actually gives me a limit, right? So the limit when x goes to phi, so what is x over square root of phi squared minus x squared? X approaches phi from the left, so this is actually phi minus, right? So x takes values less than phi. So this is always positive, this is always positive. So the slopes are all positive, right? So when I approach x is equal to phi, this actually goes to plus infinity. So what does that mean? If I draw a tangent to y of b at x is equal to phi, it is going to be vertical, right? It's going to be a vertical line. It's going to be a vertical line. So the problem arises here. You see, I have a negative slope here. So this slope is not vertical. This is not vertical to the x-axis. However, this slope is vertical. So the problem arises here. So when I compare these two slopes, this actually tells me that, the bottom function tells me that the tangent to this bottom function is going to be vertical. However, this is not going to be vertical to the x-axis. So in other words, what we see is when we plot that, we see like a kink here, like a corner. So these two functions do not connect smoothly at x is equal to phi or at x is equal to minus phi. That's why we need to come up with a different mathematical function for the yt so that the egg shape is going to be smooth. And we will not see any corners at these connection points. This is what we will do next. As I showed in the last board, the parabolic curve that we proposed for this top function was good to connect this L, T, and R points. However, the connections at L and R between the top function and the bottom function are not smooth, okay? So we were seeing some corners here. So now we will try to come up with another alternative so that the top function is going to be smoothly connected to the bottom function. So the function that I would like to propose is something that I have actually thought for a while, and then I came up with this alternative solution to actually introduce a nice smooth connection between top and the bottom functions. So the function that I actually want to propose is something like this. So y top is going to be equal to a x squared plus c plus d times phi squared minus x squared. A, C, D are constants here. In addition to this quadratic term here, I've actually added another term which looks like that. So if I just look at this function here, square root of phi squared minus x squared, this is nothing but the top portion of the circle, right? However, this doesn't go through this top point, right? That's why we need this quadratic. In the end, we also see that this is an even function of x, right? It also satisfies this requirement. So the shape is going to be symmetric, right? So the main goal here is to find this a, c, and d. Before that, let's check if this is going to give us a nice, smooth connection with the bottom function. So in order to see that, we take the derivative with respect to x. Okay, so what we see here is 2ax plus, so this gives me 1/2 d, right? and phi square minus x squared to the power minus 1/2 times minus 2x. So if I write it again, this is 2 times a times x. 2 cancels, this is minus x divided by xd divided by square root of phi square minus x square. If I want to calculate this derivative at x is equal to phi, let's say, so what I will have is dy t over dx at x is equal to phi. It's nothing but limit when x goes to phi 2ax minus xd over square root of phi square minus x square, right? So here what I see is this term just goes to 2a times phi. However, this term goes to infinity or minus infinity depending on the value of d. Since I'll be looking for a function which will be decreasing here, right? So I would expect the slope to be negative. In other words, the derivative would be negative. That's why when x goes to phi, this term is going to dominate. So having this minus sign is good. So in other words, I would expect d to be positive. So we should be setting this d to be positive. So in the end, this would give me minus infinity, right? When x goes to phi. This result actually gives us a nice smooth connection between these two functions, y bottom and y top. So in other words, the y top function is going to be vertical at x is equal to phi as well. So you will create a nice smooth connection. So in the last board, we propose this function to be the top function which would make this top portion of this golden egg shape. And we also show that this function, if d is larger than 0 here, connects smoothly with this bottom function at L and R points. So now we would like to determine what A and C are in terms of D, so that this function is going to go through L, T, and R. Okay? So let's first look at R. So the point R has coordinates phi and 0. So in other words, when y is equal to 0, x must be equal to phi. 0 must be equal to a times phi square plus c. So when x is equal to phi, this is already 0. So this actually tells me that a is equal to minus c over phi square. So let's look at now point T. So when we are at point T, the x coordinate is 0, y coordinate is phi square, right? So now phi square must be equal to x is equal to 0, this is 0, then this is c plus d times phi, right? So then c is simply equal to phi square minus d phi. It's also good. In the end, what I can write is y of t x is equal to a minus c over phi square x square plus c plus d square root of phi square minus x square. So I can use the common parentheses for c. So c is equal to phi square minus d phi, parentheses, we have minus x square over phi square plus 1 plus d square root phi square minus x square. Okay? So I can multiply this term with phi square and divide by phi square. Then we will have y top function as 1 minus d over phi minus x square plus phi square plus d square root of phi square minus x square. And this is the function which would go through L, T, and R points, and it's going to connect with this bottom function smoothly at L and R points. So this result suggests that we can create infinitely many golden eggs, right? Because I have a control parameter here, D. So I can take values D larger than 0 and I can create as many egg shapes as possible, right? So what we notice here is that when D is equal to 0, what we have is, let's suppose D is equal to 0, what we have is y of t is simply equal to, so this is 0, this is nothing but minus x squared plus phi squared. And this is the parabola that was suggested initially, right? And we had problems with that, as you all know. You can actually check different d values. For example, you can check what d is equal to 1 case, or you can check d is equal to phi case and d is equal to phi square. So now I will actually show you some plots that I created for d is equal to 0, d is equal to 1, d is equal to phi, and d is equal to phi square cases. So I have 4 plots here, A, B, C, and D. So I would like you to choose your favorite egg shape. So please write it in the comments which egg shape is your favorite. A, B, C, or D. If you come up with a different egg shape, please also mention that in the comments. You can also send the plot of the egg shape you created. So these were just 4 different golden egg shapes that we can create by choosing 4 different D values. So now I would like to show you an animation where D changes from 0 to phi square. So as a homework question to you, I would like you to tell me, or you can write it in the comments, what happens if we take very large D values. For example, if you take values of D way larger than phi square, and what kind of a shape you are going to end up with. So please write it in the comments. I also put my notes on this on Patreon. I hope you like this video and Arif's golden eggs. I look forward to seeing you in the next videos. Take care. Bye.